Now we introduce new concept of regularity. So we will learn about something called regularity lemma. It is some type of pseudo-random. So what is this? So imagine that we have some vertex there, say V1, V2, V3, and say VR. And you consider some random graph. So between these two, for each pair, U and V, you flip a coin, and if this coin is head, then you add an edge. Tail, then you don't add an edge. You do that for all pairs. And say your coin is with a head with the probability P, which is positive, and tail with the probability 1 minus P. So randomly, randomly add edges. And you do that independently. So for each pair UV and then BW, UV and WX, those events are independent. And if the number of vertices is large enough, then you can check that for whatever, for any small R-partite graph, say H, then we can check that the H is in this random graph G with high probability. Here, high probability means that the probability that G contains H converges to 1 as n goes to infinity. Okay, so in this way, so random graph is a good graph for us. So our job so far was that we want to find the subgraph H in G when G satisfies certain conditions. That certain condition is so far the number of edges is at least certain threshold. That's one very natural condition. And if such a condition, if it kept, then we wanted to find the copy of H in G. And here it shows that if the condition on G is the randomness, then this problem becomes easy. But this randomness is quite strong condition. So can you find the weaker condition that still guarantees such good property? Then we should first consider why we could find H in G. What makes this random graph so good? And if we find the gist of that property, so that essence of the property, then we might be able to deal with other graphs, so non-random graph, but still satisfy the same essential property. Then that will be still good for our purpose. So one of the, that's the philosophy of this pseudo-randomness. So there are some random objects. It satisfies certain property, and we choose some of them. Then we name them as such a property, pseudo-random property. And then we explore the, all the objects that satisfy those properties. So those graphs does not have to be random, as long as it shares such a property with the random graph, a random object, and we exploit that, and then we prove something on those objects. So that's the philosophy of this pseudo-randomness. And here we will learn about pseudo-randomness is called regularity. So, in order to introduce this regularity, let's define some notion first. Let's say you have a graph G, and say disjoint subsets A and B. Let's write the density between A and B as you consider the number of edges between them, and you divide by size of A and size of B. So you have A and B, disjoint subset, and maximum number of edges between them is this on the bottom. And this is the actual number of edges. So this measures the density of edges, how dense it is. If this is 1, then all the edges are here. If this is 0, then no edges are there. If this is half, then roughly half of the edges are there. So it's measured the density. And we say that also oftentimes, if it is clear, we don't write this G, we might omit this subscript. So we say a pair of disjoint sets of vertices. We say this is epsilon d regular in a graph G if the following holds. So what we want to define is that there are some sort of uniformity, meaning that okay, it could be the case that the A and B, there could be a density half, but those half could be, this half is completely sending all the edges to here, while these vertices are isolated vertices. Then the situation here and situation here are really far away, so they are really different. So every vertex here sends all the edges possible, while here it's only sending very little. Then we don't want this. So this is a situation that will not happen in this random graph model. In this random graph model, these vertices are like symmetric in a sense that this and this essentially play the same role. So there is no point, no like real point to distinguish them. But in this case, this vertex and this vertex, there are huge difference. So we want to forbid that. And how do we define things to forbid it? So for subsets, which are not too small, so A prime and B prime are subsets of A and B, which has size at least epsilon times A and epsilon times B. And we measure the density between them, and that's very close to D. So, or we can, in our notation, we can just write this as the D plus minus epsilon. It is at most D plus epsilon and at least D minus epsilon. Then we say that this is epsilon regular pair. Epsilon D regular pair. And we say that its pair AB is epsilon regular. We don't specify D for this. It is epsilon D regular for some real number And also, we say that this is the epsilon t plus regular if it is epsilon t prime regular for some real number t prime, which is ellipsed as large as t. Okay, so it's forbidding this kind of situation. Between this and this, the density is 1, but between this and this, the density is 0. They are too far away. That doesn't happen. So wherever you go, you see, wherever you zoom in, as long as you didn't zoom in too much, the density there is very close to the entire density. The global behavior and the local behavior are very similar in such that there are some examples. Let's say you consider a complete bipartite graph. And this is what? Epsilon 1 regular. This is epsilon 1 regular for any positive epsilon. You can check. Because in this condition, epsilon is positive means that for any positive set, if you consider the density between them, that's always 1. So this is epsilon 1 regular. And this is very useful concept. So epsilon regularity is very useful. Why? There are two reasons. So one is any graph can be decomposed or partitioned. Let me write as partition into epsilon regular pairs. Let me write almost decomposed, almost partitioned. And another reason is that it is easy to one can find any small bipartite graph in epsilon deregular pair. If this, if epsilon is quite small than d. So this too is, why this epsilon regularity is useful. If you have a graph G and we want to find H inside of G, then roughly how do you do it? You use the first fact to partition G into some epsilon regular pair. This one, this one, this one. So for example, you have so in G, you partition the vertexes so that say this is epsilon regular, this is epsilon regular, epsilon regular, epsilon regular. And then you use the second fact that, okay, if you have an epsilon regular pair here, if certain conditions are met, then you can find H in here. That's ensuring that you find H inside of G, because this is G. So that's the philosophically how we can use this concept in graph embedding problems. And let's see what this actually means. So let's first see this first statement. And this is called Szemeredi regularity lemma. Okay, maybe before that, let me define this concept. We say that a partition, a P of the vertex set, this is an epsilon regular partition, we say. If the following holds. In this partition, we have Vi and Vj. So V1 to, so this partition is from V1 to say Vk. And for all ij, you consider the ones which are not epsilon regular. So you want to show that most of them are epsilon regular in a way that we choose the pairs which are not epsilon regular and we add them. And that's at most the epsilon times the number of vertices squared. Okay. So in a sense, what? This is V1, V2, V3, V4, V5. And there are many pairs that are epsilon regular. And then the pairs which are not epsilon regular, if you collect the size, then that's small. So if we take all ij here, then this is what? This is, without this epsilon, this is the number of vertices square. But it's saying that roughly only epsilon fraction of them are not epsilon regular. And then for rest of them, it is epsilon regular. So Szemeredi regularity lemma says that for the yeah, let me write it this way. So if this holds, that means that for given epsilon, there exists t. There is t0. For given epsilon, there exists t0 such that the following holds if t is at least t0. So I will just write it this way. Then what? The following holds. Then every graph C admits an epsilon regular partition. B1 to BR, with this R being bounded almost T. So this bounds on the number of parts is important. If there are no bounds, then it's trivial that you just put one vertex in each part. Then it's either H here or non-H here, but in both cases, it's epsilon regular partition. So as long as you have just one vertex and one vertex, then it's an epsilon regular partition for any positive number epsilon. So there is no point. I mean, it's not, this partition is not useful. So we bound the number of parts. So no matter how large this graph is, it doesn't matter. It could contain n vertices, and this n could be much, much bigger than t. It's okay. So the number of parts is independent of n. So that's the point of this lemma. This is independent of n, which is the number of vertices. Note that this t is, this t0 is say t. So for given epsilon there exists t such that you can do this with the m of t parts. And we know that this t is at most the tower of epsilon to the -5. And what's this tower? The tower is like power of 1 is 2, and power of I plus 1 is 2 to the power of I. So it means, so this is what? This is 2 to the 2 to the 2 to the 2 to the 2. And the number of 2's here is epsilon to the -5. So this is huge number. This is much, much bigger than the number of atoms in the universe. If epsilon is reasonably small. If we just take 0.1 as an epsilon, then this is what? It is 100,000 power of 800,000, which is huge number, ridiculously large number, but still finite. It doesn't depend on n. And so this is the Szemeredi regularity lemma, but it's kind of weaker forms. And usually we use this Szemeredi regularity lemma as the following form. So there are actually several forms which are all equivalent that's used in different situations. So what we can do is instead of considering only epsilon, we consider two parameter epsilon and t. And t is an integer. And usually when I write Greek letter, then that's a number smaller than 1. And usually when I write the alphabet, that's integer. Then every graph G admits partition B1 to BR as follows. 1 is that the number of parts is between small t and large t. But sometimes we don't want the number to be too small. So we can put the lower bound as we want. But if this lower bound is large, then t also grows with it. So this upper bound also grows with t. So this is determined by epsilon and t, small t. And 2 is that this equitable partition means that the size of bi and bj differ by at most 1. So it's almost same size. And this bi and bj is epsilon regular. We don't know the density, but it's epsilon regular for some epsilon d regular form, some positive d, some non-negative d. This holds for all ij except at most epsilon times r square pair. And so before, here, the partition you get, we don't know whether this epsilon regular partition, we didn't know whether this set and this set has same size. They could have different size. One of them could be small and the other one could be huge. We didn't care. As long as, the fraction of not epsilon regular pair, if you add their fraction, it is small, then that was okay. But here we can further ensure that they all have the almost same size. And we can count the number of pairs which are not epsilon regular. Because now, all the sets have the same size. So for each pair, the number you add here are almost same. So this bound is as well as, it's almost same as bounding the number of pairs. But this is more organized form of this regularity lemma. And in fact, we can even, upgrade this to the following. So instead of just saying that there are at most epsilon r squared pairs, we can get more local information. The pair for each I, so you specify one of the parts, and this pair is epsilon regular for all j except at most epsilon r in the set. So for most of the j, it is epsilon regular. So before on here, it didn't say anything about how these non-epsilon regular pairs are distributed. For all we know, it could be that there are bi, and then everything here is not epsilon regular. That could happen, but we can actually ensure that that does not happen. For each I, bi is locally good in a sense that it is epsilon regular with bj for most of the choices. And we say that this is equitable partition. So when we say equitable partition, it's a partition that satisfies that. Okay, and in order to use this Szemeredi regularity lemma, there is also a concept that we need to, define. So if you have this epsilon regular partition, B1 to BR is given, we define the graph R, let R be a graph on vertex set bracket R, so which is the number between 1 and R, which are the set of indices of this B1 to BR. And there, what we encode is that we encode the information about the epsilon regularity pair. So Ij is an X of R if and only if this Bi and Bj is, say, epsilon delta plus regular. So this is epsilon d regular for d bigger than some number delta. And what we say, if such a graph is defined, then we say this R is the epsilon delta reduced graph for the given partition. So once we have this epsilon regular partition that we obtain from the Szemeredi regularity lemma, and we know that this is like epsilon half regular, and this is epsilon quarter regular. This is like epsilon third regular, and this is not regular, and so on. We know that. And let's say here it's very sparse, so epsilon regular, but the epsilon regular. So which means it's mostly empty here, and so on, and epsilon is small. Then what? You can encapsulate the information here by considering the graph R, where you add an edge if okay. This is epsilon regular, then you add an edge. This is epsilon regular, you add an edge, epsilon regular. And this is not epsilon regular, so you don't add an edge. This is too sparse, you don't add an edge. Then this gives us information about the graph, your graph G, and how the asymptotic structure of G, how its asymptotic structure looks like. So most of the edges are in here, 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 and it's losing only small fraction of the edges. So there are a few edges, but here nothing. So this was not reflective. And here, there could be many edges, but we know that these lead pairs are very sparse, very small. So it's losing the information about those edges, but it's still keeping most of the information about this edge, and then asymptotically how they are distributed. Okay, so this R contains much information about our original graph sheet. And for example, we can prove the following proposition that if we have R, let's say this is epsilon delta reduced graph. For a given partition of G that satisfy R1 to R3. Now note that this implies that, so even if you just assume these three are satisfied, then R3 is automatically satisfied. So then what? And assume this N is sufficiently large compared to this T. Say R. Yeah. Then what happens is that every degree of R, we can get the information. With every degree of R, we can get the lower bound as every degree of N minus some small number, as long as you take this delta epsilon or small. Then you can get the lower bound on the every degree of R. In other words, this R inherits the every degree of G. More precisely, inherits the lower bound on the every degree of G. So if G has certain every degree, at least something, then R essentially has the same lower bound, proportionally same lower bound. Okay, I will not prove this proposition, but it's not difficult, so you can just check yourself to make yourself more familiar with the concept of this regularity and this reduced graph. Also, the following lemma will be also useful, showing that this epsilon d regular pair acts as I explained before. So its local behavior are almost uniform. So wherever local you see, so you see here, and what's happening here, and then what's happening here, and what's happening here are almost similar. So if you have a epsilon deregular pair there, and let's say you take a subset B with the size not too small, then what you can show is that there are most of the vertices in A stands the correct number of edges to B. So you count all the vertices which stands either too many edges to be prime or too little edges to be prime, and that's only small fraction. So later this will be useful for us. You have A and you have B. Then if you take B prime, which is not too small and not too big, not too small, and big is possible, then for most of the vertices here, we send the right number of edges to B prime. Only 2 epsilon fraction sends wrong number of edges. So how do you prove this? Let's say A negative is the vertices which sends 2 small number of edges. And A plus is the set of vertices sending too many edges. Then what do we know? If one of them is too big, then what? From our definition, if you take A minus and B prime, you can compute the density between them. Because this A minus sends 2 little number of edges to B prime, it will be small. So you just count the number of edges and then compute the density. Then what? This is smaller than so this is smaller than D minus epsilon. But what did we say? We said that this is epsilon deregular pair. That means whenever you take however you take a subset of this, A prime and B prime, which has size at least epsilon times B and at least epsilon times A, then density between them should be at least D minus epsilon. But what? This has size at least epsilon A and this has size at least epsilon B, but the density is smaller than D minus epsilon, a contradiction to the definition of regularity. Okay, so what? So we conclude that this should be smaller than epsilon times A. Similarly, A plus is also smaller than epsilon times A. So total, you take the union, then you get this stat, and that's at most 2 epsilon times A. So this lemma will be useful later when we show that this concept of epsilon regular is useful for graph embedding problem, finding subgraph problem. So we have learned this part, the Szemeredi regularity lemma, that any graph can be almost partitioned into this epsilon regular pair. And next time we will learn about some lemma that's saying that if this epsilon regularity is useful for subgraph problem. And then we will learn about some application of this regularity lemma to prove certain things. Okay, then I will see you in the next video.